Okay, but now let's get to math from these more philosophical considerations. And let's do this as concretely as we can, talking about an explicit example that includes most of the technical issues that you have to talk about. So the example is fx equals sum n equals 0 n squared plus n and x to the n. And you could be given, and I would venture to guess that you'll see something very similar in the homeworks and possibly the final, is that a standard form of question is that show that blah defines a continuous and continuously differentiable function on the domain, say, -1, 1. And this is, you could criticize this statement as a little bit cryptic or misleading because, okay, it is really, the statement is really asking you to prove that this defines a continuous and continuously differentiable function. But what you actually do in the proof is something seemingly very different. It's asking you to do certain checks and apply certain theorems in a way that you always do. And these words, defines, continuous, continuously differentiable, these are really code words that are not asking you to say directly what they're doing, but instead to do something that proves these claims. So verify the assumptions of the relevant theorems. And these are the theorems that we have talked in the last 2 weeks about. And don't worry, I'll remind you what these theorems are so you know exactly what to apply. So I'll tell you what you really want to do, what I really want you to do. First, defines. What do I mean when I ask you to show that something defines a series, defines a function? Well, it is this sort of corpus delicti issue that you have to prove that the series converges. So part A of these problems, if I haven't explicitly given you a part A, is that defines. And this means that prove that the series converges on -1, 1. Because if it converges, it then defines fx is so-called well-defined for each x in -1, 1. This means that if I take an x in this interval, this formula really outputs a value. It doesn't output a value unless the thing actually converges. Otherwise, it's just f of x is this nonsense, but the nonsense has to be something real. So defines really here means that you prove that the series converges. It's code word to saying that the series converges. And you could say pointwise converges, but I don't want to emphasize this point too much here because usually you do it actually by proving that something converges uniformly. So because pointwise convergence is actually very rare to prove, usually it's some form of uniform convergence that you've proven. Okay. Now, continuous. Well, what does it mean to show that something is continuous, converging continuously? Well, we'll get to this soon in the detail. It really is asking you to say that Fn converges to F uniformly. The partial sums converge uniformly as n goes to infinity on some subintervals. So -a, or a in -1, 1. So specifically, like in a picture, you have this interval, and you have this interval, sorry, I'm repeating some of these things because my internet is sometimes going in and out, -1, 1, but usually the convergence doesn't hold on the whole thing, but you get convergence for all, uniform convergence on so-called compact parts of this set. whose union is the whole thing. And on those sets, you get uniform convergence. Now then we use this fact that a uniform limit of continuous functions is continuous. So really, we're not proving that the limit function is continuous by any kind of epsilon delta consideration. We're proving the condition of a theorem that the partial sums are converging uniformly. And similarly, in the third thing, when I ask you to prove that this is continuously differentiable, assuming that you've already done A and B, I'm really, again, also only asking you to apply a theorem. And for that theorem, we have to get that the sequence, these indices should start from 0, of partial sums Fn prime, and these are the derivatives of the partial sums. Now, if you have a finite sum of functions, the derivative goes inside. So the derivative of the partial sums is the sum of the derivatives. And the condition, and I'll remind you soon, is that this converges uniformly to some function g. It doesn't have to converge a priori, or we don't know that this is converging to the derivative. We have to just prove that it converges to something as n goes to infinity. And again, on these intervals, minus AA, or A in 0, 1. Now, we'll go through this carefully in a bit, but now the crucial thing in B and C, what we also use, and this also plays a role in A to some degree, is Weierstrass M-test. Because to get these uniform convergence statements, again, we're not going to do an epsilon n proof. We will not choose an n that gets this convergence. Instead, we will apply a theorem, and the general theorem to this avail will be Weierstrass M-test. So all of this series discussion is and what you do in the proofs is actually you apply these theorems in these standard problems. Of course, there can be other problems like the problem 4 on the exam. But generally, you have these 3 parts, A, B, and C. And we'll see these 3 parts. And so how do you prove these? Let's state first the Weierstrass M-test. This was what we did last Wednesday. I won't repeat the proof now. You can go back there or also read this in the book. So a series of functions, and again, this is a formal expression before we establish any sort of convergence, but this theorem is the way to establish that converges. It converges uniformly on some interval of R if there exists constants Mn such that you can bound the function by Mn, and this has to occur uniformly for all x, but with a bound that can depend on n. So if you get if you have such a bound, and you have that these bounds, some of these bounds converge, and these are now real numbers Mn. If you have this as finite, then you know that the series converges. And for us, I already gave a certain, for power series, usually why the series converges is really because it is like a geometric series. So we'll see what this is soon. So we'll look at Mn of the form Ca to the n, where A is in 0, 1. And we'll get that this finiteness comes from geometric series. So these are the tools. Okay, I want to, before I go into that, I want to do an example. So this is the code that is on CCLE. And I ran this code. It's a little bit of a different function. There's a -1 sign here, minus n squared. I thought it made a nicer picture, so that's why. But okay, here are partial sums. Okay, there's an extra picture at the, well, yeah, extra picture here at the beginning. So first constant series, then I'm adding the quadratic term. The linear term here gives me 0 because of the minus, actually, yeah. linear term. This is adding the linear term, which is 0. This is adding the quadratic term. This is adding the cubic term. And as you notice, every time the function changes shape a little bit. First, initially quite a lot, because the first few terms are quite big, but then the changes become more minor. The quadratic term, the quintic term, the sixth degree term, and after that we start to see that the differences become very minor. And eventually we converge to this picture. Now, remember that I said that the convergence happened, we're looking at the interval -1, 1. Now, what is happening in these side-by-side pictures is that here you have an interval from -2 to 2 on the left-hand side, whereas on the right-hand side you have -0.5 to 0.5. So, okay, initially there's not a huge difference what happens, but once you go to more than, say, 5 terms, you start noticing a big difference. The right-hand side is converging nicely. The range stays around -3 to 3. These ranges on the right-hand side stay controlled, but you see on the left-hand side what's happening. You get values like -8,000, 4,000, and everything between -1, 1 in this scale, because the y-axis is so huge, is becoming like constant. It's not seeing it. It's seeing only the behavior, what happens outside the interval of convergence, where the function is becoming very big. And this is where the convergence is not happening. You don't have convergence outside the interval -1, 1 because things are going off to infinity. Now, something that makes this a little bit more clear is a familiar picture that you probably have seen before is the Taylor series for sine. If you take the leading order term, you only have the linear term. Then you have the cubic terms because you only take odd terms. Then fifth degree terms. And adding every term makes this function look a little bit more similar to the sine. And I'm only plotting here between -4 and 4. But after about 5 terms, we see that we have converged quite quickly. At least the shape of the graph is already correct. In the case of sine, we could take any interval that we want, because it turns out that the convergence happens everywhere, in contrast to this example where the convergence happens only in -1, 1. So with power series, we see through these examples that there's a region of convergence outside of which usually things blow up, become very big or very small. Any questions so far? Okay. Let's switch back to the file and let's go through our example. Okay, so we had this series n² plus n, x to the n. And we saw in our examples, even though there was that minus sign, that if x is bigger than 1, then this series seemed to not converge. And what is causing this is that if we have a series converging, then a basic thing that you need is that the coefficients are going to 0. And what's the cause of this is that the coefficient an is the difference of the partial sum Sn and Sn minus 1. This is equal to an. And throughout, Sn is this partial sum. You're summing from k equals 0 to n ak. So this is n terms, and this is excluding the nth term, and that's why you're left with an. And absolute values, but you can take them away as well. But by Cauchy-ness, this has to go to less than epsilon. Therefore, the elements have to converge to 0. How can a sum of things converge unless the elements converge to 0? So in our case, this means that before we talk about convergence, we should make sure that n² plus n, x to the n, is going to 0. Well, if you are absolute value of x is bigger than 1, then, well, limit x to the n is going off to infinity. So in that case, limit n² plus n, x to the n, is not going to 0. So can't converge. Indeed, we must have then that x is absolute value less than 1. Now, a common thing with power series is that when you get such a setting is actually these endpoints will cause a problem. they, in a sense, the bounds there are not as good as inside, as we will see. So we have to look at subintervals, minus AA for A in the open interval 0, 1. So we're excluding the endpoints by looking inside. And they're usually excluding. Sometimes you can say things about the endpoints. This topic is the concerns in Towel. He talks about Abel's theorem. I will not talk about it in the core lectures. I'll do a little supplementary video to talk at least about the statement, but we will not focus on that. That creates some trickiness at the endpoints. Okay, so what we saw from our example is that if you plot these power series, what you will usually see is outside the radius of convergence, you'll get something big, and that corresponds to this failure to converge. On the boundary, the behavior is unpredictable, and there also numerical error might screw things up. And inside of that, you'll get relatively quick convergence. So in practice, I mean, if you at least up to pixel accuracy, the picture won't really change after 10 terms. Of course, it depends on the coefficients a little bit, but in practice, the picture won't change. These are usually not the methods that converge to these functions the fastest, so you don't use them to approximate functions too much. For example, there are much better ways of computing sine and cosine than using the Taylor series. So if you really care about efficiency of your numerical program, you would not be using these methods, but for simulation purposes and simple functions, relatively few terms are needed. I guess the machine precision should say for sine and cosine should already come in 10 to 20 terms. It goes at least in the interval, some bounded interval. So there's an issue with some of the power series that the coefficients are tricky because they include factorials. So they're difficult to add. So there's many numerical issues actually in practice in computing them. So it's somewhat of a theoretical tool, is what I want to say. Okay, so now let's remember, we're still working with our example n squared plus nx to the n. So let's check the things that we said. We want to check the defined aspect from -1 to the 1. And there will be a crucial lemma that we use to estimate. I mean, these terms have the form n to the n squared, or some polynomial, times something that is geometric. And because x has absolute value less than 1, this geometric thing is decaying very fast. And now what you might remember from 131b, 1a, or before is that if you have a geometrically decaying thing times a polynomial, the geometric decay is what matters. So this lemma is what helps us to say this rigorously. It says that if you fix a degree and if you fix a base bigger than 1, then there always exists a constant such that n to the d is less than a constant times b to the n. And this is true for all n. The constant has to depend on b. The smaller the b, the bigger the constant, or the higher the degree, also the bigger the constant. But what this is saying is essentially that a polynomial grows slower than all geometric powers. So how do we use these in estimates? And this is usually the crucial estimate that we will use in a lot of the time, is that we want to estimate these terms, n squared plus n, x to the n. And so let's fix an a and fix an x inside the interval minus AA. So, and then we want to estimate these quantities. So let's look at, by lemma, we know, and we'll choose b, and this choice will become soon clear, 1 over square root a. It will give us that there exists a constant, now omit the subscripts, such that n squared plus n is less than or equal to c to the b n for all n. Now you notice that the lemma says that this is true for n squared and n individually. So you would, if you wanted to prove this carefully, you would have to get two different constants, and the c would be the sum of those two constants, because this is, you sum up two estimates of this form. But I want to abbreviate. So lemma gives us some constant, so this true is for all n. This is true. Now, okay, what does that give us in our case? And remember that we're applying this to the Weierstrass theorem. So we want to estimate absolute value of fn of x, which is n squared plus n times absolute value of x to the n. Well, this here can be estimated from above by cb to the n. And the second term we can estimate from above by a to the n, where since we use the fact that absolute value of x is in the interval 0a, because x is in the closed interval minus a, actually, including a. Okay, so now we have a power of two things, and it becomes apparent why we chose this b, because let's write out b as what it is. It is square root of a to the power minus n, a to the n. And what is this? This is this square root of a, it takes half of the power. So this is minus n over 2. And then the sum of the powers is a to the minus n over 2. Sorry, a to the n over 2. And this is our mn. And it might be better to write this as c square root a to the power n. And what is the lesson? This is between 0 and 1. So mn is really a geometric series. So as a geometric series, we know that mn converges. This is like a comparison test that we were talking about last time. So now we get that the sum of mn converges. So by the m test, we get uniform convergence on the interval minus aa for all a in open interval 0, 1. So we get convergence on these intervals that are strictly inside minus 1, 1. And their union is the whole thing. So we get convergence on the entire thing, because we can always choose an a such that x is inside this interval. Or x should be imagined to be somewhere there. Okay, so now let's get to continuity. We know that now Sn converges uniformly to the infinite limit on this closed interval minus aa. Zero, 1. And Sn is continuous. Why? Because, well, Fn, these are polynomials. Fn is equal to an, Fn is equal to, in our case, n squared plus n, x to the n. So this is clearly continuous. The sum of continuous functions is continuous. So this infinite sum is a uniform limit of continuous functions. We got uniform convergence there. So therefore, by theorem, that I will just soon remind you, f is continuous. So what did we use here? We used the fact that if you have continuous functions on any metric space, so Fn is continuous, and Fn converges uniformly to f, then the limit function is continuous. One important thing here is, like from the numerical simulations that you see, you do not converge uniformly on the whole interval. Uniformly. But you converge on parts of the interval. And continuity is a local thing. So if you are inside this interval, so if you have an x between minus 1 and 1, you choose an a so that this interval completely swallows that point. And you get continuity on this interval. But because x is contained in that interval, in the interior of that interval, you get continuity at x. So there's an inner argument like this that's hiding. But we do not get the uniform convergence on the whole interval -1, 1. And why is that? Because our estimate falls apart if we get too close to 1. We need the fact that we can choose b to be strictly bigger than 1 by the choice of a being less than 1. Because square root of a is less than 1, and the reciprocal is bigger than 1. But if we have a is equal to 1, nothing happens. Our proof doesn't start. Okay, what about differentiability? Well, let's see. Now we have a theorem that requires, okay, we have the uniform convergence, but we have to say something about the derivatives. And I'll remind you of the statement soon. But let's look at the derivatives of the partial sums. Now this is a sum of derivatives of fn prime. And in our cases, what this gives us is by differentiating n times n squared plus n x to the n minus 1. Now this is another power series. So we can use the same techniques to estimate it. It's again of the form a polynomial times geometric. So we can hope to find the similar estimates by just replacing the factor in front. So by lemma, again, there exists a constant c so that n squared plus n is less than or equal to c times b to the n. Now this c will be different from above, and then we get the same bounds. We get the same bounds, c b to the n, a to the n. So here are same choices as above. c b to the n, a to the n. This was c square root of a to the minus n, a to the n. And this gave us, this is equality. So c a to the n over 2. And again, by Weierstrass m-test, we get the same convergence because c times a to the n over 2 is still a geometric series, just with a difference constant c. The value of c doesn't matter because we are only talking about convergence. We don't care what value it is. So we get that fn is differentiable since we have the assumptions of a theorem. And I'll remind you what we have. There are two main ingredients. Sn converges to f, and Sn prime converges to G uniformly. And we also get that the derivative can be expressed as a power series. And usually we want to have x to the n there. So we shift the indices. So we replace n by n plus 1 to get x to the n there. And then that replaces the coefficient of n plus 1. Okay. Technically, this shifting would make the index here go to -1, but because the first term goes away by the quote, and when n equals 0, you get 0 coefficient, you don't have to take that into account. So what was the theorem that we used here to get differentiability? If you have a pointwise convergence of differentiable functions whose derivatives converge uniformly and derivatives are continuous, then the limit function f is continuously differentiable by fn. Now, there are two things that we established. This we established by Weierstrass m-test in part B, and this we established in part C by differentiating the series using similar bounds as in part B. But these red things, differentiable and continuous, these are automatic because our functions are, our partial sums are polynomials. Any questions? I was a little optimistic of my battery, so I have to move. Okay. Okay, so there are three theorems: Weierstrass M-test, uniform limits of continuous functions is continuous, and this theorem about derivatives that you have to apply a lot of the time. There's also the theorem about integrals, but in this problem that didn't come up. That you will practice in the homework this Friday, actually. So actually you can say more. We talked about the derivative, but you can say about higher order derivatives as well. Now let's recall f is smooth or infinitely differentiable if f has a derivative f prime, if f prime has a derivative f double prime, and inductively and the nth derivative of the function, so derivative, 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 n times, if these all exist. And then by repeating this argument that we did in part C, we can actually show that the function f is smooth. Why is that? Because if you differentiate this, what do we get? Every time we get a factor of, we get a power that goes up front. So first we get an n, then we get an n minus 1, n minus 2. If we do it k times, we get up to n minus k minus 1 times the previous coefficient, and every time the power gets dropped by 1. So if we do it k times, it drops by k. Now, this is exactly like before. We have a polynomial. Specifically, if you merge all these coefficients to 1, you can estimate this from above by a constant times n times 2 plus k. The n to the n squared comes from that. And because there are k terms here that are all smaller than k, we get that that is bounded by n to the k. So really, by lemma, this is again bounded by another constant times b to the n, a to the n. Okay, a to the n minus k, but that k doesn't really matter for us. So you can repeat the argument from before to get, again, differentiability of arbitrary order, because always you get the same form, polynomial times something geometric. And you can always apply M-test to get uniform convergence on subintervals. Any questions at this point? Okay, so our time is almost up. We will finish certainly a lot of this on Wednesday. Now, I want to state some lemmas. So we had this lemma from above that was very useful. For every d and b positive, you can estimate polynomial growth from above by geometric code, by some constant. And I will probably discuss this proof in a second. But I want to say something about other tools as well. So we've seen these, and we'll get back to these on Wednesday. Now, to get these estimates that we want, sometimes things are, if we don't have polynomial things, the proper tool will be a limit superior. This is a concept, it's a little bit technical to state, but it should be thought of as some so-called best eventual upper bound. And this replaces our bounds for things like polynomials. And the idea is that, okay, the sequence is, suppose it's bounded, it has some upper bound, but as you move along the sequence, you get better bounds that form a decreasing sequence. These bounds are always a supremum starting from some index. Now, if you take a limit of a decreasing sequence, that limit always exists, and this limit is called the lim sup. Now, this is a difficult concept, but I want to extract say two things about it. We won't study it very much because it is a little tricky, but this is enough for most purposes, and this was actually enough also on the exam that we had. So this is useful in contexts where the limit does not exist. If we're talking about general power series, we don't know if these limits exist, and therefore we need to talk about lim sup instead of lim. In general, lim equals lim sup if both exists. And the main lemma that we will use, and the only fact really about lim sups that we will use, is that if we know that the lim sup is less than m, this is the same thing as saying This is equivalent to saying, but we'll only use one direction here, that this implies the second. It means that M is an eventual upper bound, meaning that there exists an index N such that capital N, such that AN is less than capital N for all indices after that. So this is really this statement translated. It's a convenient way of expressing this statement. And this is how mostly in analysis people use lim-sup. A lot of the time. It's really just a convenient abbreviation for this. But with this statement, we can state the root test that will play the crucial role in proving that power series converge. Namely, if you have a series AN, be any series, then it converges if we know that the nth root of the absolute values has a limiting value less than 1. And as said, we have to say this with lim-sup because we don't know that this is going to less. And I mean, where does this nth root come from? Well, we want to say if we have that absolute value of n is less than or equal to some b, and when you raise this to a power n, what you get is absolute value of an is less than or equal to b to the n. And this is the geometric series. So really this root test is hiding within it the geometric series test. So we'll see that more on Wednesday. And maybe I'll just say one, actually, yeah, I will not do the proofs on any of these. I'll just conclude with why these lemmas are important, and we'll have time on Wednesday to discuss this. These tests are really perfect for looking at series that we want to look at. Because if you take the nth root of something like this, what do you get? Well, you get the nth root of absolute value of an. This is the kind of the expression that we were looking at. And you get nth root of absolute value of x to the n, but this is absolute value of x. So the behavior of this is controlled by the behavior of that, up to a factor multiplying by a constant. And when we're doing the convergence analysis, we are fixing x in a certain interval. So if we have the root test, the convergence of power series is really based on this first estimate. And we'll see how that comes on Wednesday. But let's end here for now with a roadmap that we'll do on Wednesday. And if there are any questions, I'm happy to answer them.